What if the rules of quantum mechanics you learned in school were actually missing a crucial piece for describing the real universe? A universe where particles can spontaneously pop into existence, vanish into thin air, or where trying to label them as this one or that one is, well, utterly impossible. Today on The Deep Dive, we're unlocking that missing piece. We're embarking on a journey to explore the concept of the Fock space. It's a revolutionary mathematical framework that didn't just solve some of the biggest head scratchers in quantum physics, but literally laid the groundwork for modern theories like quantum field theory. Think of it as the master key, really, to understanding why the universe behaves the way it does at its most fundamental level.
And you're absolutely right. This isn't just some abstract mathematical playground, not at all. This is the underlying language that explains everything. I mean, from why your phone works to how light travels, even to the incredible stability of stars. Stars billions of times more massive than our sun. This deep dive, it's going to reveal the profound elegance and, frankly, surprising simplicity behind the seemingly complex behavior of particles, from the tiniest interactions right up to the grandest cosmic structures.
Okay, let's unpack this then. Our story starts with what we might call standard quantum mechanics, often referred to as first quantization. This is the framework where you describe a classical system, maybe like a single electron orbiting a nucleus, by promoting variables like position and momentum into quantum operators. And it works beautifully when you have a fixed number of particles, describing a hydrogen atom, for example. Perfect. In this view, if you have, say, n particles, their combined state lives in a mathematical space that basically stitches together the possibilities for each individual particle.
Right, and this is where the core problem immediately pops up, that fixed number of particles assumption. While it's powerful for certain isolated systems, it dramatically breaks down when we factor in Einstein's special relativity, remember E-mc fall. It tells us mass and energy are interchangeable. And this isn't just theory. It means if you have enough energy, particles can literally be created from pure energy or annihilated back into energy. Think of an energetic photon, a particle of light, spontaneously creating an electron-positron pair. Happens all the time. Or an electron and a positron meeting and annihilating, turning back into photons. These aren't exotic exceptions. They are fundamental, everyday occurrences in high-energy physics, and they are entirely, completely outside the descriptive capacity of that fixed particle framework.
And it's not just in, particle accelerators or cosmic rays. Even in more mundane, non-relativistic settings, that fixed particle framework quickly becomes, well, clunky. Consider an excited atom emitting a photon that's fundamental to how we get light, or a material absorbing light, or even phonons, which are basically quantized vibrations in a solid, like sound waves treated quantum mechanically. All of these phenomena involve the creation or destruction of these quantum packets of energy or vibration. So a theoretical framework that insists the number of particles never changes. It just can't provide a natural or fundamental description of these ubiquitous processes. It feels forced.
And this raises an even deeper, maybe more subtle problem. We could call it the quantum conundrum, the fundamental indistinguishability of identical particles. See, in the classical world, if you have two identical billiard balls, you can, in principle at least, paint a tiny dot on one and track which is which. But in the quantum realm, if two electrons or two photons have overlapping wave functions, you cannot tell them apart. It's not just difficult, it's physically meaningless to ask which electron is which. And this principle means that if you swap two identical particles, the probability of finding them in a certain configuration must remain absolutely unchanged. The physics can't depend on your arbitrary labels.
Right, and this seemingly simple requirement about indistinguishability forces particles into two very distinct social groups, you could say. We have bosons, think photons, gluons, the Higgs boson. They have integer spin. For them, if you swap two identical bosons, their collective wave function stays exactly the same, sign and everything. There's sort of the gregarious particles. They don't mind sharing the exact same quantum state. In fact, as we'll see, they kind of prefer it. Then we have fermions, like electrons, protons, neutrons. They have half-integer spin. For them, swapping two identical fermions changes the sign of their collective wave function. It flips from positive to negative or vice versa. They're the exclusive, or maybe antisocial particles. And this behavior, this sign flip, has profound consequences for the very structure of matter.
Exactly. And the problem with the old fixed particle Hilbert space was that you had to impose these symmetries, well, by hand, ad hoc. You'd calculate everything and then manually force symmetrization for bosons or anti-symmetrization for fermions. It's like trying to fit a square peg in a round hole, conceptually awkward, computationally intensive.
Yeah.
Just not elegant. It wasn't an intrinsic feature of the theory itself. What we desperately needed was a framework that inherently incorporated these fundamental symmetries and, critically, allowed for a variable number of particles. I mean, think about it. An expression that describes a quantum superposition of states with different particle numbers, like a state that's partially one particle and partially two particles at the same time. That concept is totally meaningless in a fixed particle framework, but it's absolutely essential for describing quantum processes where particles pop in and out of existence.
Okay, here's where it gets really interesting then. The resolution to all these challenges came with a major paradigm shift, moving from first quantization to what we now call second quantization. First quantization, like we said, is about quantizing the properties of individual particles, their position, their momentum. But second quantization, it takes a completely different approach.
Exactly. It's a subtle but profound conceptual leap. Instead of trying to describe where each individual particle is in second quantization, you quantize the field that describes the particles themselves. So the state of the system is no longer about listing the coordinates of each of your n particles. No. Instead, it's specified by listing the number of particles, the occupation number, that occupy each available single particle quantum state.
Wow, okay. That is a huge shift in perspective. The primary question evolves from where are these specific n particles to how many particles are currently occupying each available quantum slot or state. And this elegantly solves the indistinguishability problem, right? Because the framework simply doesn't care which specific particles are where.
Exactly. Just how many are in a particular state. The identity is irrelevant.
And it brilliantly handles variable particle numbers using these new mathematical tools called creation and annihilation operators. Their whole job is to change those occupation numbers.
Yep, allowing the system to naturally move between states with different total particle numbers. Creation adds one, annihilation removes one. It's built right in. Mathematically, this elegant structure is built on the concept of the Fock space. You can sort of picture the Fock space as this grand infinite library. But instead of books, each room in this library is dedicated to a specific number of particles. There's a room for 0 particles, the vacuum, a room for 1 particle, a room for 2, 3, and so on, all the way up to infinity. The total Fock space is simply the combination, the direct sum, mathematically, of all these rooms. And at the very heart of this infinite library is the crucial vacuum state, often written as 0 Oz or azu. Now, this isn't just empty space or nothingness in the classical sense. No, it's the fundamental foundational state. It's the quantum canvas, if you will. It's the state from which all other states in this infinite library can be generated by applying these creation operators. It's the quantum zero point from which particles are literally born into existence within the theory.
So, okay, this full Fock space sounds like an incredibly flexible mathematical construction, but how do we get from this abstract idea to the actual particles we observe in the real world, with their distinct behaviors, the gregarious bosons and the antisocial fermions?
That's where the profound connection between a particle's intrinsic property, its spin, and the required symmetry of its wave function comes into play. This connection is dictated by something called the symmetrization postulate, closely related to the spin statistics theorem. For bosons, integer spin particles, the relevant space is the bosonic Fock space, F plus H. It contains only totally symmetric states. And this symmetry means any number of identical bosons can occupy the exact same single particle quantum state. No problem at all. Think of them as the ultimate social butterflies they love to bunch together. This gregarious behavior, mathematically enforced by the symmetry, is the root of many remarkable macroscopic quantum phenomena we actually see. Now, for fermions, half-integer spin particles, we use the fermionic Fock space, FH. This is constructed from totally antisymmetric states. The amazing consequence of this antisymmetry requirement is mathematically unavoidable. If you try to put two identical fermions into the exact same single particle state, the mathematical description simply collapses to the null vector 0. It's impossible. This is the mathematical origin of the famous Pauli exclusion principle. No two identical fermions can simultaneously occupy the same single particle quantum state. They are the exclusive particles, inherently antisocial in this quantum sense. And this fundamental rule, baked into the Fock space, defines the very structure of matter around us.
It's really incredible, isn't it, how these seemingly abstract mathematical rules about symmetric for bosons, antisymmetric for fermions, lead directly to the tangible real-world phenomena we observe and measure every single day. This is where physics truly gets exciting.
Indeed it does. These fundamental choices in constructing the Fock space dictate the statistical behavior of vast ensembles of particles. This gives rise to two distinct forms of quantum statistics. For Bose-Einstein statistics, that symmetric nature of bosons means there's actually a statistical enhancement for multiple particles to occupy the same state. They like to clump. This tendency for bosons to bunch together is responsible for things like Bose-Einstein condensation. BEC. Under the right conditions, a macroscopic fraction of the particles collapses into the single lowest energy quantum state, forming a giant, coherent matter wave. This explains phenomena like superfluidity in liquid helium-4, where it flows without any friction, and of course, the coherent, monochromatic light produced by lasers, which is essentially a condensate of photons. On the other hand, Fermi-Dirac statistics, driven by the Pauli exclusion principle, forms the absolute bedrock of chemistry and condensed matter physics. The exclusion principle dictates that as you add electrons to an atom, they must fill successively higher energy orbitals. You can't just pile them all into the lowest state. It's like filling seats in a stadium from the bottom row up one person per seat in a given state. This enforced shell structure is precisely why we have the organization of the periodic table of elements. It's what enables the rich variety of chemical bonds that form the basis of all molecules, and ultimately, all life. And in bulk matter, like metals, electrons fill energy levels up to a maximum known as the Fermi energy. This creates a surprisingly powerful quantum mechanical pressure called degeneracy pressure.
And this degeneracy pressure, it sounds like something that might only matter in a lab, maybe. But you mentioned cosmic implications earlier. It has truly cosmic significance, right?
Oh, absolutely. It's fundamental to astrophysics. Imagine the sheer, unimaginable gravitational force of a dying star trying to crush itself completely out of existence under its own weight. What stops it? Not chemical bonds, those are long gone. Not even nuclear forces in many cases. It's the Pauli exclusion principle, enforced by the fermionic nature within the Fock space, pushing back with an immense quantum pressure. It's fermions refusing to occupy the same state. This pressure literally holds up dead stars against their own immense gravity, preventing them from collapsing further, potentially into black holes. It's responsible for the stability of white dwarfs, which are supported by electron degeneracy pressure, and even denser neutron stars, supported by neutron degeneracy pressure. The journey from an abstract symmetry postulate about tiny particles to the grand stability of stars across the universe. It truly illustrates a remarkable and beautiful causal chain in physics.
So the real power of this framework, the Fock space, comes from what we call the algebra of many-body systems, basically how we actually work with and manipulate states within this space. And the central tools here are the creation operators, often written as a dagger, and annihilation operators, written as A.
Yes, these are the fundamental actions you can perform within the Fock space. They're like the basic verbs of this quantum language. An annihilation operator, A, associated with a particular single particle state, essentially removes a particle from that state, decreasing its occupation number by 1. If the state is already empty, well, applying A just gives you 0, the null state. Nothing happens. The vacuum state, as we mentioned, is specifically defined as the state that is annihilated, set to 0, by all annihilation operators. The creation operator, A dagger, does the exact opposite. It adds a particle to that specific state, increasing the occupation number. The amazing thing is, any state in the Fock space, no matter how complex, can be built up by starting with a vacuum state 0 and applying a suitable sequence of these creation operators. Similarly, any physical process particles scattering off each other, decaying, being emitted or absorbed, can be precisely described as sequences of these fundamental creation and annihilation operations acting on the states.
And if you just want to know how many particles are in a specific state without changing anything, you use the particle number operator, often written NO, which is basically the creation operator immediately followed by the annihilation operator for that state NST. It essentially asks, can I remove a particle? And if so, put it back, and the result tells you the occupation number.
That's right. Now, for bosons, the fundamental rules governing how these operators interact with each other are called the canonical commutation relations, or CCR. These relations essentially say things like, applying two different annihilation operators in sequence doesn't depend on the order, A, AJ, E0. Same for creation operators. AI, AAJ, U0. The key non-zero relation is between creation and annihilation for the same state, AI, AAJ, J. This basically encodes the adding one or removing one property. This easygoing nature of the commutators means you can stack as many bosons as you like into the same quantum state reflecting their symmetric nature. Think of it like an infinite party where everyone's welcome to dance in the same spot. This algebra also reveals a really deep connection. Each quantum mode of a free bosonic field behaves mathematically exactly like an independent quantum harmonic oscillator. Adding a boson is like exciting the oscillator to its next energy level.
What's really fascinating here, though, is that for fermions, we have a completely different set of rules. Instead of commutators, we use anti-commutation relations, the CAR. They're defined using the anti-commutator, which is A times B plus B times A. That plus sign makes all the difference.
All the difference in the universe, literally.
This subtle change in the algebra has monumental consequences. For fermions, the anti-commutation relations state things like AAAA, which is 2AI. Now look closely at AAAA, that's AAAA plus AAAA, which is 2AA, so this must be 0 according to the CR.
It means AAA has to be 0. You apply the creation operator for the same state twice, and you get nothing.
Exactly. You cannot put two identical fermions into the exact same quantum state. The algebra forbids it. This simple algebraic statement, AAAIAO, built into the very structure of the Fock space for fermions, is the second quantized expression of the Pauli exclusion principle. The entire structure of atoms, the diversity of the periodic table, the stability of matter itself, it can all be traced back to this fundamental no-two-alike anti-commutation rule. It's incredibly powerful. This transition to second quantization replaces these cumbersome multivariable wave functions with this incredibly potent and, dare I say, elegant algebraic structure using operators.
Okay, so with this powerful new language in hand, let's look at some of its truly astonishing applications, just to show how broad the utility of the Fock space really is. First up, arguably the biggest, quantum field theory, or QFT. This is the framework that successfully merges quantum mechanics with special relativity. And instead of viewing particles as tiny individual billiard balls, QFT describes them as quantized excitations, like ripples or quanta, in an underlying quantum field that permeates all of space-time.
And the Fock space provides the perfect state space for this view precisely because it naturally accommodates changing particle numbers, which, as we said, relativity demands. A scattering process, for example, where maybe two incoming particles collide and transform into four outgoing particles. That's simply described as a transition from a state in the two-particle sector of the Fock space to a state in the four-particle sector. It's natural. And the QFT vacuum, hello, is far from being a tranquil void. Because of the Heisenberg uncertainty principle applied to fields, it's actually this dynamic, bubbling sea of virtual particles constantly being created and annihilated. Their fleeting existence isn't just theoretical fiction, they leave measurable fingerprints on reality. Things like the Casimir effect, this tiny but real attractive force between two uncharged conducting plates in a vacuum, or the Lamb shift, a tiny correction to atomic energy levels, both caused by vacuum fluctuations.
But it gets really complicated when these fields actually interact, right? I remember hearing about something called Hagg's theorem. Doesn't that essentially say the simple Fock states of bare particles, the ones created directly from the vacuum by a single AO, don't actually represent the physical particles we observe in experiments? So, like, an electron isn't just a simple electron excitation.
Precisely. That's a very deep and subtle point. When particles interact like an electron interacting with the electromagnetic field, photons, the simple non-interacting Fock space picture breaks down rigorously. A physical electron, the thing we actually measure, isn't just a bare electron excitation of the electron field, it's that bare electron constantly surrounded by a fluctuating cloud of these virtual photons and electron-positron pairs from the vacuum. It's dressed by its interactions. To connect the theoretical results of our QFT calculations, which often involve these bare states and interactions, to the physical reality we observe in experiments, a sophisticated procedure called renormalization is absolutely essential. Now, historically, it might have seemed like just sweeping infinities under the rug, but it's actually a very well understood and brilliant set of techniques. They allow us to absorb the unavoidable infinities that arise from these interactions into a redefinition of fundamental physical parameters, like mass and charge. This ultimately yields finite, testable predictions for observable quantities that agree with experiments to astonishing precision. I mean, sometimes to 1 part in a billion, or even better. It's one of the triumphs of modern physics.
Okay, shifting gears a bit, let's talk condensed matter physics, the physics of solids and liquids. The Fock space is utterly indispensable here too, I gather. Think about something seemingly simple, like the free electron gas model for metals. Isn't that a foundational starting point?
Absolutely foundational. And the ground state of this system, the lowest energy state, is beautifully described in the fermionic Fock space. It's a state where all the single particle electron energy levels are filled up perfectly, right up to a certain maximum energy level, with 0 electrons having energy above that point at 0 temperature. This filled sea of electrons is known as the Fermi sea, and understanding it is the basis for explaining nearly all the electronic properties of metals, their electrical conductivity, their heat capacity, their magnetic response. It all starts from the Fermi sea and the Pauli principle. It also underpins our understanding of phenomena like superconductivity, where under certain conditions, usually at low temperatures, electrons, which are normally these antisocial fermions, can form bound pairs called Cooper pairs. These Cooper pairs effectively behave like composite bosons. And what do bosons like to do?
They like to condense into the same state.
Exactly. These Cooper pairs can then undergo a kind of Bose-Einstein condensation, forming a macroscopic quantum state that allows electrons to flow through the material without any electrical resistance whatsoever. A truly remarkable collective quantum phenomenon, all enabled by the Fock space description.
And the impact of Fock space isn't limited to the subatomic world or solids either. It's also completely revolutionized our understanding of light itself, the very photons that make up our universe in the field of quantum optics. A photon in this view is basically just a single quantum of excitation in the quantized electromagnetic field.
That's the modern picture, yes. And the Fock space allows us to describe a rich variety of different quantum states of light, going far beyond classical descriptions. For instance, Fock states, sometimes called number states, represent light with a definite, precise number of photons, like n-Phe. These are highly non-classical states. For example, a state with a definite photon number n has a completely undefined phase. This means the average or expectation value of the electric field is actually zero. It's lumpy light, not a smooth wave. Then there are coherent states. These are the quantum states that most closely resemble a classical light wave, like the steady, predictable beam from a good laser. They're actually eigenstates of the annihilation operator, interestingly enough. And perhaps most intriguing for applications are squeezed states. These are states where the quantum noise, the inherent uncertainty in one observable property of light, like its amplitude, is reduced below the standard quantum limit at the expense of increased noise in another complementary variable, like its phase. These are crucial for making incredibly high-precision measurements, like in gravitational wave detectors.
And it's not just theory. The role of Fock states in quantum information and quantum technologies is absolutely exploding right now. Single photon Fock states, one day, are fundamental building blocks for things like quantum key distribution, aiming for unconditionally secure communication. And higher order Fock states, like 203, etc., are critical for pushing the boundaries of things like boson sampling, which is a specific type of quantum computation, and also for achieving enhanced metrology using quantum effects to measure things with unprecedented sensitivity, beating classical limits. Now, if we connect this to the even bigger picture, the mathematical structure of the Fock space has apparently found surprisingly deep resonance in fields seemingly quite distant from physics. I heard something about logic.
That's true. It's fascinating. The mathematical construction of the bosonic Fock space, in particular, has been identified as a canonical model for something called the exponential modality, often written with a or bang, in a system of logic called linear logic. In linear logic, unlike classical logic, premises are treated as resources that are consumed upon use, unless they are explicitly marked with this modality, making them renewable or reusable. The ability to create an essentially unlimited number of identical bosons in a given state within the Fock space is the perfect physical analog of a renewable resource in this logical framework. While fermions, constrained by the Pauli exclusion principle, one per state, perfectly model non-renewable resources. It's an incredibly intuitive and elegant link between the fundamental rules governing quantum particles and the very foundations of logical reasoning about resource usage. Quite unexpected.
So looking ahead then, the Fock space formalism isn't just some historical artifact. It remains a vibrant and absolutely essential tool for physicists today. Researchers are constantly developing new computational methods, right? Like tensor networks to handle the often enormous size, the exponential growth of the Fock space dimension in computational many-body physics. This allows us to simulate increasingly complex quantum systems, like materials with strong electron interactions. We're also still working on constructing mathematically rigorous frameworks for truly interacting QFTs, which, as Hagg's theorem hints, are far more complex than the simple Fock spaces we use for free fields. And of course, a massive area of research is engineering specific quantum states within the Fock space for quantum technologies, from precisely crafting high-order Fock states of light for quantum communication and sensing, to manipulating entangled states in many qubit systems, which can be thought of in a Fock-based context, for quantum computing.
And finally, perhaps the deepest frontier in the ongoing quest for a theory of quantum gravity, the theory that aims to merge gravity with quantum mechanics, the very concept of a particle, and therefore the Fock space built upon it, might turn out to be not fundamental. It might be an approximation or something that is observer-dependent, like an Unruh or Hawking radiation, or perhaps even emerge from a more fundamental, background-independent description of reality, where space-time itself is quantized. This suggests that while the Fock space has been incredibly powerful and has unlocked so much understanding of our universe, it might not be the ultimate language for describing reality at its deepest, most foundational levels. The story might still be unfolding.
Wow. What an absolutely mind-bending yet clarifying journey we've taken today. From the fundamental limitations we hit with the initial quantum mechanics, through the elegant solution embodied by the Fock space, and seeing its pervasive influence across basically all of modern physics, explaining particle behavior, the structure of matter, the very nature of light, the stability of stars, and even surprisingly, reaching into the foundations of mathematics and logic. It truly feels like the language of the quantum universe.
It really does. And this raises, I think, an important final question for you, the listener, to ponder. If the particles we observe are ultimately just emergent excitations, just ripples of underlying quantum fields, and even the vacuum, the nothingness, is actually this dynamic, effervescent sea of quantum fluctuations, what does that truly say about the fundamental stuff of reality? And how might our understanding of concepts like the Fock space continue to evolve as we keep probing these deepest questions about the nature of the universe?
Absolutely fascinating things to think about. Thank you so much for joining us on this deep dive into the Fock space. We really hope your curiosity has been piqued to perhaps explore more about quantum field theory, condensed matter physics, or quantum optics. Until next time.